Welcome back to Business Statistics. We're now in section 6.3 where we're going to talk about finding confidence intervals using a student's t-statistic. Now, I told you last time that the big idea here is that I essentially lied to you during the last day of class. I didn't lie to you, but in some ways it was a little misleading in that we had this formula, which was x bar minus zc times sigma over the square root of n is less than mu is less than x bar plus zc times sigma over square root of n. But this whole formula relies on one big assumption that is just never safe to make. And that big assumption is right here in sigma. It's that mu is the population standard mean, and we're saying we don't know the population mean, but we do know the population standard deviation. That seems a little crazy, and in fact, it's generally not the case. So what we're going to do is we're going to make a small modification to this formula, and then we'll learn how to use it, and it's going to work a lot like the last problem, but just with a few modifications. In short, what we need to do is we need to change the sigma, and so I'm going to go ahead and write our modified version, and then we'll come back and talk about it. So instead of sigma, we're going to use S. What's the difference between sigma and S? They both mean standard deviation. The difference is sigma is standard deviation for the whole population. S is a standard deviation for just those people you studied. So this you always know because you had people to study, you had some data. Sigma you don't always know. In fact, very rarely would you know it. Now the problem is we can't just keep everything else in the formula the same. What we have to change is we have to change our critical value. And instead of being ZC, we're going to use something called TC. So this is going to be our new confidence interval formula. We're going to use something called TC, and we're going to use S. And there we go. But in order to do that, I need to introduce something called a student's t-distribution. So the student's t-distribution is a lot like a standard normal distribution. So here's a standard normal distribution. The difference between the student's t-distribution is because we're using S instead of sigma, it could be that our standard deviation is not quite perfect. So we need to be a little bit more careful than our standard normal. So what a student's t-distribution looks like is it looks a lot like this. The only difference is it's a little bit flatter. So it's just kind of a little bit of a flatter version. So this would be a t-distribution. And it turns out that there are actually a lot of t-distributions. Which t-distribution you use depends on how big the sample size is. So this might be a t-distribution where n is small. And as n becomes bigger, your t-distribution becomes less and less flat. So if I use a bigger n, I might get something that looks like that. So now I might have something like this. It's always going to stay above. So I might get something like this where my t-distribution is less flat, and it starts to look more and more like an n. And then by the time n gets really, really big, I get something that's really, really close. This is a very big n. Very big n. So what you'll find is that as your sample gets bigger and bigger, your t-distribution starts to look more and more like your standard normal distribution. So once we get really big numbers, whether we did this test the way we did in the last section or whether we do it the way we did in this section, doesn't make a really big difference. This shape to it is what we call degrees of freedom. And so our degrees of freedom and we are going to always calculate degrees of freedom the same way, at least right now in this class, and that is degrees of freedom, we just take n minus 1. Why n minus 1? Well, in some ways, degrees of freedom is how many things are free to be every number possible so that you can and still come out with the same average. You all have done this before when you've taken a class. So you have a class, the class has 5 exams, you've taken the first 4 exam grades, and you know you need an average of 90. And so you could figure out what grade do I need on the fifth test to give me an average of 90. Notice those first four tests can be any grade that you want. They can be 90, 80, 95, 75, or they can be 95, 97, 98, 93. So they can be any numbers you want, and you calculate the fifth one to make an average of 90. So in other words, 4 of the tests are free to be any number, but the 5th test has to be the right number to make the average come out to be 90. As you all know, sometimes that score that you need for that 5th test is not possible. Sometimes you calculate your first 4 tests, and then your 5th test, you realize you need 125 on your final to get an A, and then you realize that's not going to happen. Hopefully that doesn't happen in this class. Hopefully you feel like you can get the grade you want when we're all done. But okay, so degrees of freedom are always 1 minus our n, because all of them are free to be any number you want, but that last one is not free. So we have n minus 1 degrees of freedom, and the degrees of freedom is what affects the shape. So the bigger the degrees of freedom, the closer our shape looks here. There's a nice little story with the t-distribution that I think is worth telling. The t-distribution was created by a statistician that worked for a private company. And the private company, as private companies normally do, they like to keep all of their information, anything their employees learn or create, they keep it kind of within their company. They don't want to share it outside of their company. And this makes sense, right? If you're Apple, you don't want to share your secrets with Samsung for them to go use them to create phones that are then going to compete with you. And so any sort of field you're in, you kind of want to keep the things that your company learns secret from other companies. And this was the case with this individual. But he started creating these tests in order to study the things within his company. I don't remember the details. You could Google students' t-distribution and it would give you all the details about him and his story. But the end of the story was that he realized that the students' t-distribution would be useful for people outside his field, and he realized that this was actually a really important thing for society. Maybe people in medicine, maybe people in other fields would really benefit from this, and this would be really useful. So he wanted to share it, but he was worried about the company, about his company being upset and maybe he losing his job or something like that. So what he chose to do is he chose to publish his results and his discovery of the student's t-distribution under the name student. And so he was just a student of statistics. And so he would write a paper and the only name he put on it was student. And so to this day, it's called Student's T, not named after him, but named after the fake name that he gave to his papers. But okay, the good news is we can calculate the t-distribution using our technology. And so we had a bunch of old ways that we did it for the normal distribution. And we're going to have kind of the same types of methods for t-distribution. And so again, I'm going to focus on the app because that's the easiest thing for me to show, and I can be pretty confident that you all have it. But feel free to use your other devices as necessary. So if you have a normal distribution, if you're using Excel, if you remember normal distribution, we had 2 commands. One was norm.dist, and then over here we just use t.dist, and it does the exact same thing. You give it your value and it gives you your probability. Again, you give it your value and it gives you your probability. And then we had our norm, our inverse, .inv. I think that was it. I'm not completely sure. And t.inv. Let me put some question marks besides this. If you need to, you can log in study hall hours and we'll get sorted. I think that's the right command. I bet if you start typing it, you would see it in there. So Excel, we use the exact same commands, except you're going to have your T command. And you'll notice in your menu when you start typing in, you'll have to enter, instead of entering the mean and standard deviation, you enter your degrees of freedom. And so it works the exact same. Okay, next for a calculator, we have, we had normal CDF. And over here, we'll have T CDF, and it'll work the exact same way. So normal CDF, you give an upper and a lower, and then your mean is standard deviation. Here you give an upper and a lower, and then your degrees of freedom, and the numbers come out the exact same. And then we had inverse norm, and here we have inverse T. And so inverse T works the exact same as inverse norm. Inverse norm, you tell it the probability and it gives you the value. Inverse T, you tell it the probability and it gives you the value. The only difference is we're working T distributions instead of normal distributions. Finally, for the app, which is what I'm going to grab and we're going to use, for the app, you go to the normal menu over here. And then over here, you just go to the T menu. You just scroll down and find T. And then you'll find a funny letter, which is new, which looks something like that. Let's see, is that what I never can write a new very well. But looks something like that, and new is your degrees of freedom. So let me power my app up, and we'll look at how to find some things. All right, here is my app. So now that we've powered our app up, we can come and find, so there's normal, and you just keep scrolling down and you find T. And so here's the T distribution. Notice we've got the new, which is kind of this funny, almost V-looking thing. Oh, I didn't do a very good job drawing that, did I? Let's see if I can make it look a little bit better. There we go, that kind of looks like a new. It's one of those letters I haven't drawn very often. Okay, so this is just our degrees of freedom. So let's just pick a degrees of freedom. How about like 10 degrees of freedom? And then notice, just like the other app, if I put an X here, if I put, say, X equals 1.5 and hit enter, then what that's going to do is it's going to give me the 1.5 and give me all the probability to the left of 1.5. And notice that's 0.9776. By the way, what if I make this number bigger? If I make that number bigger, you'll see how my distribution became wider and fatter. And if I make it smaller, like for example, if I make it 3 and do 1.5 here, then you'll see how my distribution becomes, oh, it actually is, I guess it looks the same every time, but it actually is much fatter here. So sorry about the visuals, but at any rate, we've got the same thing. We put our probability here and get all the values, and then you can control your probabilities here. And similarly, if you want to go backwards, all we have to do is put, if we want to find a spot that has 90% to the left, you put a 0.9 here, and so 1.63 is that value that has the 90% to the left. So it works the exact same as the normal distribution app. We're just using T instead. So if you're confident with your app, I think you're good to go. Okay, now that we've done this, let's just remember, what is our formula going to look like? So our formula for confidence intervals is this formula that we wrote down earlier. So it's x bar minus TC times S over square root of n is less than x bar plus TC times S over square root of n. And these TCs are found the exact same way we did ZC a second ago, except we used the T button on our Excel, on our calculator, or on our app. So the only difference is which one we're using. Okay, let's tackle 6.3 and see if we can make some progress on it. So 6.3, we're back to this problem where we have a bunch of flies, and we have our 7 flies that we've caught, and we kind of want to figure out what's their size, how big are these flies. And so we have them all here. The first thing we need to calculate is we need to calculate the average size of our flies. So we need to know what is the average and what is S. If you don't remember how to do this, you use either your calculator, or you can use either your calculator or Excel. And there are also apps online, but I haven't searched for them. So you use your calculator, Excel, list all these out, do the average button, and do the standard deviation button. And I know the answer, so why don't you go ahead and pause and do that without me, and then unpause once you get it, and we'll see what we got. What I got was 6.54 for my X bar and 0.579, so 0.58 for my S. So that's what I got for those two numbers. So that means I'm now well on my way to finding my 90% confidence interval. So if I want my 90% confidence interval, I'm here, and notice I already have my x bar to go in that spot. I have my s to go in that spot. So what do I still need? I still need to know what n is, and that's not too hard. N is just how many samples I have. And so n is just the number of flies. And I have 1, 2, 3, 4, 5, 6. I had 7 flies. So n is 7. And now the only thing left is to figure out what is TC. And TC is what requires a little bit of thinking, but it's not too bad because we're at 90%. So that means I want to draw this picture. I have a t-distribution, which I'm going to draw them just the same as a normal distribution because they have the same shape. They're just a little bit wider. I have a t-distribution. I want this area right in the middle between TC and negative TC. I want this area to be 90%. If you remember, I can't put 90% in my calculator because if I put 90% in, it doesn't stop at the other side. It keeps going forever. So I need to figure out, what do I want that number to be? Well, this side over here is 5%. So I need to use 0.95 for my calculation. And both the calculator and Excel do the same thing. You have to use 0.95. So I'm going to get my app out. My degrees of freedom needs to be 1 less than 7. My degrees of freedom is 6. Right? So if I come over here, degrees of freedom equals 6. And then I want to do 0.95 because I want 95% to be to the left, and that'll give me 90% in the middle. So now if you look, I've got 95% here. If I cut that off, I'd have 90% in the middle, and 1.94 is what I get for that answer. 1.94. All right. Oh, if you hear that ringing, I don't know if it's going to show up or not. My son just finished his homework, so he rings a bell when he finishes his homework. Okay, so let's grab our formula, and I'm going to rewrite it real quick, and then I'll put everything into it. So we've got x bar minus TC times s over the square root of n is less than mu is less than x bar plus TC times s over the square root of n, and now I just plug those numbers in and come up with my value. So I've got 6.54 minus 1.94 times 0.58 divided by the square root of 7 is less than 6.54 plus 1.94 times 0.58 over the square root of 7. And now I just have to get all this successfully typed into my calculator. And I'm going to start with just this multiplication part, because remember, we have to get our order of operations. You have to multiply before you can subtract. So let's just do 1.94 times 0.58 divided by the square root of 7. You get 0.43 for that section. So I've got 6.54 minus 0.43 is less than mu. Oh, I forgot. I missed the middle part here, didn't I? There we go. So less than mu is less than 6.54 plus 0.43. And now I just have to do those two additions. 0.54 minus 0.43. And that's going to give me 6.11 over here. And then on the other side, I get 6.97. And so here is my confidence interval. And that, oh, sorry, I'm off the screen. You can't see me. But here's my confidence interval. And so that gives us some picture of what that means. So if somebody says, how big are your flies? Well, we know that between 6.11 and 6.97, and you'd say there's a 90% chance that the size of the flies, that the actual average size of a fly is between 6.11 and 6.97. So they're somewhere in that range. All right. Well, let's flip the page over and let's try problem 6.4. Why don't you start on part A on 6.4 and see if you can be successful? And so do the normal thing, pause your screen, give part A a go, see if you can get everything put into your formula correctly, and if you can, then that's a good sign that that everything's making sense. And if you can't, that's okay. Just come back and we will get it worked out. All right. I'm glad you tried that. I hope that it went well. So we look at part A. All we have to do is now we're still looking at the same formula. So we have that formula again. And so we're just asking ourselves what are the different pieces that go into it. So we need to know X bar. We need to know S. We need to know N. And we need to know TC. And for this problem, most of them are just given to us right out front. So X bar is 62.3. S is 4.7. And N is the number of cars. So N is 50 cars. And then TC is what we have to go calculate. So I'm going to do the same thing. I've got this picture. We want a 95% confidence interval. So that means I want this to be 95% in here. So how much do I need on this side? I need 2.5%. So that means I'm going to put into my app or into my calculator, I'm going to put 0.975 is going to be the area that I'm looking for. What are my degrees of freedom? My degrees of freedom are 1 minus 50, so my degrees of freedom are going to be 49. 49. So let's grab our app here and figure this out. By the way, I didn't say last time, but if you're doing this at home, if you're doing it on Excel or on your calculator, you're going to be wanting to use the inverse operations. You're going to want to use either the inverse T command on your calculator, or the t.inv command on your Excel, because we're going backwards, because I'm telling you the probability and you're figuring out X. So you want to do it backwards. You're needing the inverse command. So we're going to put 49 in here and put 0.975 in here and hit enter. And what you can see is our number 0.2009 is the number we've got. So let's write let's go 2.01. So see how we've got our 97.5%. So that means 95% is 0.2001 was the answer. Okay. All right. So we've got all those things out. Now we're ready to start putting it into our formula. What if I don't write the formula out again? What if I just put it directly in? So we'll go 62.3 minus 2.01. Tell you what, I'm really running out of space. Yeah, let's just erase all of that. 62.3 minus 2.01 times 4.7 over the square root of 50 is less than mu is less than 62.3 plus 2.01 times 4.7 over the square root of 50. Now I'll calculate all of those in and see what I get. And so I've got clear 62.3. Oh, hold on. Let's do the inside part first. 2.01 times 4.7 divided by square root of 50. And that's going to give me 1.33 is that part. So I've got 62.3 minus 1.33 is less than mu is less than 62.3 plus 1.33. Sorry, I ran out of room. And let's subtract those out. 62.3 minus 1.33 is going to give me 60.97. And then on the other hand, I've got, if I add instead of subtracting, I get 63.63. Okay, so this is what I get for my confidence interval. So my confidence interval is 60.97 on one side and 63.63 on the other side. So that means if somebody comes and says, how fast, so somebody comes up to you and says, how fast do the cars move on the highway? You could say between 60.97 and 63.63. So between 61 and 63.5 are kind of where it is. And if somebody says, well, how confident are you in that? You would go, I'm 90, based on our study, I'm 95% confident that the actual average speed is somewhere within that range. All right, let's move over to part B of this problem. And part B from this problem, everything stays the same except it said, what if we treated it, instead of S, what if we treated it like a sigma? And if we treated it like a sigma, then we would be doing the same formula, except we'd be doing the formula for last time. So I want to ask the question, that is, how wrong was our answer last time if we would have done it the other way? And if we treat it like sigma, then that means we have ZC's instead of S's. So we'll have to go and find out what ZC is. So the only thing that changes on our formulas are we have, so the only thing that changes, our X bar is the same, our sigma is the same, except it's a sigma, not an S, and our N is the same. The only difference is this very last value, which was a TC, is now a ZC value. So let's go calculate that. And the way we'll do that is we'll do the same calculation, except we'll use the normal button. So we'll use normal, 0 and 1, and we'll put 0.975 in here. Hit enter on that, and we get 1.96 is going to be ZC. So now when I come up here, I've got a 1.96 instead of the 2.01. And that's going to change that value, and oh, not that one. And then it'll change all, and then it'll change these as well. So this is 62.3 plus, and then we'll get those numbers. So let's calculate those. Let's calculate the 1.96 times 4.7 divided by the square root of 50. And that's going to give me 1.30. And then over here we've got 1.30. So now if I subtract, I get 62.3 minus 1.3. And I get 61 on this side. And then on the other side, I get 63.6. So if you look, what do you notice about comparing those answers to these? The difference is only 3/100ths of a range. So you got basically the same range. This kind of shows us that for this problem, there wasn't a big difference whether we solved it the way we did in the last section, which I kind of said was wrong, or the way we did it in this section. As a general rule, we use the t-distribution because it's not that much harder to use, and we're a little bit more comfortable with those answers. But what you notice, right, is that if we used the normal distribution, we would have almost the exact same interval. Why did they end up almost the same? The answer goes back to that picture I drew at the beginning, and that is that if you have a normal distribution, the bigger the n gets, the closer it looks like a normal distribution. And so for this problem, n was equal to 50, and so since n was equal to 50, the difference between this black line and this red line were not very significant. They were roughly the same thing in both cases. If the number of cars had been quite small, if we'd only had 5 cars or 10 cars, then we would have seen a much bigger difference between our two answers. But when you get a pretty large value of n, the difference between the two answers is quite small. All right, section 6.5 we're going to skip, and it's a really interesting section. What section 6.5 does is it allows us to ask a question, and that is, what if I knew how big I wanted my confidence interval is? Could I pick the right n to make my confidence interval that small? So what you notice is the bigger that n becomes, the larger your sample is, the narrower and narrower your confidence interval becomes. So the question is, can I choose n to be big enough that my confidence interval is as small as I want it to be? And the answer is yes. So if you're doing a problem, and say you were doing this car problem a second ago, and you wanted, instead of our confidence interval going from 61 to 63, so this has a range of about 2.6. If I wanted my confidence interval to have a range of, say, less than 2, say if I wanted to just have 1 on each side from the middle, or 0.5 on each side in the middle, could I figure this out? The answer is yes, I could figure it out. And the way I would do it is I would take this formula that I had. I would take this part that we call the error, and I would try to decide how big I want n to be to make that error small enough. And that turns into an algebra problem. This is actually really interesting, and it's super useful. It's one of the more useful things we do in statistics, but due to the time constraints, missing class, working online, we had to make some decisions to cut some things, and so this is one of them. Do your homework, and next time we're going to hit a section which is a really big section, and it's the other really big idea. So the two big ideas that we're going to hit, one is called confidence intervals, and the other is called hypothesis tests. And so the next 2 or 3 videos are all going to be focusing on hypothesis tests and getting you confident with that. So thank you very much, and I'll see you later.